going to start our second short session of orals from the workshop posters. And this time we will have Sookyung, I hope I don't pronounce it too wrong, from Lawrence Livermore National Laboratory, and she will be presenting a work on tracking extreme climate events.
Hello everyone, and my name is Sookyung and I'm a postdoc in Rice Segmentation Lab. So I will explain briefly about the conventional method of extreme climate. In conventional methods of extreme climate event detection, actually human experts detect the hurricane one by one from simulated data. So this is incredibly labor-intensive process. To save computing power and human effort, we are suggesting data-driven methods to detect extreme climate events. To do this, we should understand the unique challenges for this extreme climate event problem. Firstly, extreme climate event detection, the number of target objects that we would like to detect is not known previously, so we cannot parameterize it as the input. Also, the target object is defined by the spatio-temporal dynamics and complicated correlation between multiple climate variables like wind speed, cloud fraction, and precipitation, and so on. In this work, we formulated the problem of tracking hurricane as the density map prediction of the hurricane using convolutional LSTM model. Basically, input is the climate image with multiple channels of climate variable and the output of the heat map, density map of the hurricane. In this way, we designed the problem as the pixel-wise regression problem from climate image to density map of the hurricane. This is basically a schematic of our LSTM hurricane tracking model. At each time step, the multiple-layered convolutional LSTM predict the density map of the hurricane at corresponding time, and also based on the spatial-temporal historical information of the hurricane data. As the baseline, we compared our result with CNN-based detection model. The CNN-based detection model of the hurricane is existing and widely used method in climate community. To do this, we first collect the labeled data of the hurricane and pre-train the detection CNN of the hurricane, and basically scan through that pre-trained CNN across the global image of the hurricane. So we can generate the heat map of the hurricane by this way, but we didn't use the temporal information for this method. So this is our main result from our proposed combo LSTM tracking model. Those top three rows represent the input channel, which is the eastward wind, northward wind, and precipitation. Can you see the little dot, which is the hurricane event? And its time interval is around 3 hours. And this ground truth is the synthesized heat map from the historical hurricane report. And this is the output from our model. You can see that very strong correlation between output and the ground truth. And from that heat map of the ground truth and output, we reconstruct the trajectory of the hurricane. This black is the ground truth trajectory of the hurricane, and the red dot is the trajectory from the output of model. But from this baseline detection CNN, we can see lots of false positive instances. That is probably because we didn't consider the temporal information to get the heat map. So our quantitative analysis of the output also shows that combo LSTM-based model got the higher precision score and the F1 score than CNN baseline. To sum up, we proposed the combo LSTM hurricane tracking model, which can able to capture the pixel-wise spatial-temporal pattern of the hurricane. Our result shows that our proposed combo LSTM tracking model has better precision than baseline CNN model. Although this is not novel in computer vision, this is novel in climate community, and we can make high impact using state-of-art deep learning method for new climate data. Thank you.
Thank you very much. Is there any questions in the the audience for this. Okay?
If you, yeah, sorry. If you come to us again, if you train it with the sequence of a certain length, will it generalize to longer sequences, or do you have to train it with the full sequence length that you're going to?
So, are you asking that the sequence that I trained using comparison will be that?
Sorry, I didn't hear.
So I think the question was whether, so you train it with a given length of sequence, correct me if I'm wrong, of input images, and whether it would generalize to longer sequences. So if it would work if you input longer sequences.
Oh, in our case, we just fix the time length as a 10 time step. It is according to the 30-hour data. But for this, our used case of the hurricane, 30 hours is enough to learn the pattern of the hurricane.
And I have just a follow-up question on this. So would it be easy to extend your work for prediction of upcoming, so because for now it's just tracking, and would it be easy to extend it for prediction?
Yes, I put the post about my prediction result, but I didn't put the PowerPoint because of the time limit. We predict the trajectory of the hurricane for next 5 time step based on the 10 time step. So it has strong accuracy of the prediction as well. Hurricane trajectory is easier than pedestrian tracking because the movement is kind of straightforward based on the climate data.
Okay, thank you very much.
Thank you.
And now for the last oral presentation of the workshop, I please ask you to welcome Aisha Urooj, who will be presenting a deep look into hand segmentation.
Please for the introduction. Good evening, everyone. So today I'm going to talk about this hand segmentation problem. So detection and segmentation of hands is useful for many applications such as hand object detection and visual recognition and so on. Particularly in first-person vision, it is important to accurately segment hands of the camera viewer as well as the person with whom he is interacting with. The RGB datasets targeted at this task are usually corrected in the constraint settings, which results in the poor performance when we apply those models in the real world. Also, one of the well-known challenges to the task is similar appearance occlusion, where hand is usually occluded by other body parts or it is occluding them. To the best of our knowledge, the similar appearance occlusion problem has not been addressed with the dataset. To address these limitations, here is our contribution. We introduce Ego-YouTube hand dataset, which has pixel level annotations for recorded in unconstrained settings. And we also introduced hand over face dataset, which is a small dataset. It has pixel level annotations and it actually addresses that similar appearance occlusion problem. We also performed extensive experiments to highlight the challenges for this task. Ideally, we would like to detect all hands in the first-person videos recorded in the unconstrained daily settings. To meet this objective, we need pixel-level annotations in the real world and for images and videos. So here we can see the sample images from Ego YouTube hand dataset. We have frames with variations in environment, such as indoors as well as outdoors. We downloaded 3 egocentric YouTube videos for this dataset, and which are 3 to 6 minutes long. We labeled the hands with the hand type, like they have pixel level annotation, but they have hand type left or right. Also, we have the viewpoint variation, that whether the hand belongs to the first person or third person. Number of participants in this dataset are also vary. So after cleaning the video frames, every 5th frame was annotated, resulting in 1290 video frames annotated pixel level. The heat map on the right, it shows the special hand appearance, and we can see that more yellow the heat map is. It shows that most of the time hands were appearing at those positions in the dataset. This histogram is actually showing the hand size distribution in the dataset. Next, for the hand over face dataset, here are some sample images. This dataset is has 300 images from the web, which has pixel level annotations, again for left or right hand. And this image has, like, we tried to minimize the bias, and we have images for different ethnicities, age, and gender. The heat map for this dataset shows that most of the time in this dataset, hands are occurring towards the center of the image. I'm going to show why it is important. If we compare these heat maps with the existing datasets like EcoHeads and GDA, we can see that the author time in those datasets hands actually like whenever we collect dataset in the bias settings, it is biased towards only the few locations in the image, which makes it to perform poor when we apply it to the real world environment. We also attempted to measure the generalization capability of the datasets by evaluating the models across different unseen datasets. We study the correlation between head size and the network performance. We also study the failure cases for the trained network. You can download these datasets from the provided GitHub link here. This work was published at CVPR this year. And to read more about this work, please refer to the paper analysis of head segmentation tool. Thank you so much, Yana.
Thank you very much for the talk. Are there any questions? Yes, please.
Why yet another data set for EcoHeads? What is, I didn't understand what is the difference with respect to the GDA?
Oh, so the GDA dataset, it has first person, the camera here is doing certain activities in a constrained environment. So the environment is not changing, the elimination condition is constant. So when you train the network on these kind of dataset and you apply it to the real world, these networks actually have poor generalization capability. They don't perform well in real world. And we have experiments for this, and you can read more about it.
Thank you very much for your talk. Please give a last round of applause before we move on.